Chapter 6, Section 3 is about applying linear functions. So by the end of this lesson, you should be able to interpret linear graphs. So you can model many real-world situations with linear equations. Recall that a graph of an equation shows you all of the solutions. However, for a discrete real-world situation, not every point may represent a reasonable value. So remember we talked about the difference between discrete and continuous. Discrete is when you would just have points that could make a line, but you don't connect them because it doesn't make sense to have whatever values are in between here. It has to do with when we're counting things or people that we can't cut in half or in fractions of any kind. So let's say we have a sporting goods store that sells cans of tennis balls, and there are 3 tennis balls in each can. The coach of the tennis team is buying supplies. We need to write a linear equation that relates the number of cans to the total number of tennis balls. Graph the function that models the situation. So we need to figure out our 2 unknowns, the 2 things that we don't know the answer to. So the 2 things we don't know are the number of cans and the total number of tennis balls. And then we need to figure out which one's the independent variable and which one's the dependent variable. So remember, independent is what I can change. And I'm going to change the number of cans that we buy. And because of that, that's going to change the total number of tennis balls that I have. You can think of the number of tennis balls as dependent on the number of cans that I buy. So then if I want to write a linear function, we normally start off with y equals, how is the total number of balls related to the number of cans? Well, there's 3 in each can, so I could represent that with 3x. However many cans I get, multiply it by 3, that's the total number of balls. So then, if I go to graph this thing, this is number of cans down here, and then this is how many balls. So if I buy 1 can, I end up with 3 tennis balls, 2 cans, I end up with 6, 3 cans, I have 9, 4 cans, I have 12. Now usually we would draw this, we would connect the dots, we would be done. But think about this problem. It doesn't make sense to buy like a half of a can. We can't come in right here and figure out how many tennis balls that would be because it's impossible for us to do that. So we're going to leave this as just random dots on here because this is discrete. It doesn't make sense to have stuff in between. So let's do another one with a discrete function. So this one talks about students in a 9th grade class, and they drew the following graph to represent how much money would be in the class fund after washing cars at a fundraiser. So if we take a look here, we have 2 things that we got to ask. The slope and the y-intercept. What do they mean? So let's take a look at our graph. The y-intercept's easiest to spot, so let's talk about that. The y-intercept, this would be 30 here. The y-intercept is at 25. And if you look here, that's $25. That's the balance in the account. So the y-intercept of $25 tells us that we started with 25 bucks in the bank account. We didn't earn it, it was already in there from maybe another fundraiser. So let's find the slope. The slope is how much we make per amount of car. So what we have to do is we have to find one of these dots that's exactly on a crosshair. So like this one right here at 5 cars, or if we trace up, this one looks close, but it's not exactly on there, so we don't want to use that one. Another one would be here at 15. So what we're going to do is figure out how much money we made per each car. So we're going to find rise over run. So if I think about this, I went up from 25 bucks to 40 bucks, so that's up $15. Divided by 5 cars. So that means the slope is 3. So if you think about that in this situation, that means that I'm making $3 per car. If I wash 6 cars, I'm going to make $3 more than what I have here, and it's going up by 3 every time. So now these questions ask us to change the slope or the y-intercept. So B says if the graph had the same slope, so we're still making $3 a car, but a y-intercept of 15, what could we say about the fundraiser? Well, we would make less money, first of all. And it's because we started with less money. Remember, the Y-Intercept of 25 tells us that we just had $25 in the bank account before we started the fundraiser. So now this says, if a graph had a slope of 5, what could you conclude about the fundraiser? Well, we would make more money because we would be charging $2 more a car. And if you are doing 16, 17 cars, that's a lot of money. So now suppose we drew the following graph to represent how far you ride your bike at a steady rate. What is that rate? So again, we're finding slope. I want to know how much distance I cover and how much time. So again, I'm going to find a spot on the graph with a nice pretty point on it that goes through some crosshairs. And remember, slope is rise over run. So if we start at this point down here and figure out how much we rise up, we go up 12 miles. And how much we run over 1 hour, we can find our rate. It's 12 miles per hour. You could have done this with any of the points on here, like this one here that goes through the crosshairs. You'd go up 6 in 0.5, and 6 divided by 0.5 will also give you 12. So now let's say the graph had a slope of 10. What could you conclude about your bike ride? So a slope of 10 would mean we'd only get to here in the same amount of time. So that would mean that we were riding slower. Our rate was lower. It would take us a little longer to get wherever we were going, and we were basically just moving at a slower pace. So the slope on this represents how fast we're going. So that's it for the lecture. Can you interpret linear graphs? So this models the height in inches of a burning candle as a function of time in hours. You need to answer questions A, B, and C. Make sure you write down any questions you have, and we can go over them in class tomorrow. Have a good night.